Measurement feels like the safest thing we do when we try to understand the universe, because numbers give the impression that reality can be contained, compared, and ranked. That if something is bigger or smaller, heavier or lighter, older or younger, then it must also be clearer. But the deeper we look, the more measurement itself begins to behave strangely. Not because our tools fail, but because the universe does not care about the scales we impose on it. There are places where size stops meaning what we think it means, where larger no longer implies dominance, where smaller does not imply insignificance, and where numbers continue to increase even though understanding does not. The universe is filled with objects, distances, energies, and times that technically can be measured, yet refuse to become intuitive no matter how carefully we calculate them. Some quantities grow so large that adding more no longer changes their meaning. Others shrink so far that distinction itself dissolves, and in between, there are measurements that exist only because our equations allow them, even though no physical intuition survives the translation. This video is not about listing the biggest or smallest things for spectacle. It is about the strange moment when measurement itself begins to fail as a guide to understanding, when numbers still exist but no longer help us imagine what those numbers represent. We will move through scales where size becomes disconnected from influence, where distances become so vast that motion loses relevance, where times stretch so far that cause and effect blur, and where quantities become extreme not because reality breaks, but because our human sense of proportion does. These are not errors or paradoxes. They are natural consequences of a universe that was never built around human intuition. The cosmos does not scale itself to fit our minds. It simply exists, and our measurements chase it, sometimes successfully, sometimes into regions where meaning quietly slips away. If you enjoy slow, thoughtful explorations that let ideas unfold without rushing them, consider subscribing to Theories Before Sleep, where we take complex scientific ideas and follow them calmly to their limits. The first place where measurement begins to behave oddly is not at the extremes we usually imagine, but in the quiet mismatch between size and influence. We tend to assume that the larger something is, the more it should matter, that size naturally translates into power, dominance, or importance. In everyday life, this assumption works well enough. A mountain reshapes weather, a city reshapes economies, a star reshapes the space around it. But the universe does not preserve this relationship indefinitely. There are scales at which objects become enormous without gaining proportional influence, and others where things become incredibly small while remaining decisive in shaping reality. Measurement keeps increasing or decreasing, yet its explanatory power weakens, as if the numbers are still correct but no longer helpful. Consider distance on cosmic scales. We measure separation in light years because kilometers stop being useful almost immediately once we leave the solar system. A light year itself already represents a compromise between human intuition and cosmic reality, tying distance to the speed of light simply because ordinary units fail to convey scale. But even light years quickly lose meaning. When distances stretch into millions or billions of light years, motion itself becomes deceptive. Two galaxies can be separated by a distance so vast that no signal sent today will ever reach the other, not because space is empty or obstructed, but because expansion carries them apart faster than information can travel. The number describing that distance is accurate, yet it no longer describes a meaningful relationship. Separation still exists mathematically, but interaction has vanished. Measurement survives while relevance disappears. At this point, size stops functioning as a guide to consequence. A galaxy cluster can be larger than anything humans can meaningfully imagine, yet its internal motions may be so slow and its future interactions so limited that its sheer scale adds nothing to its influence beyond a certain threshold. Making it larger does not make it more powerful in any practical sense. The number grows, but the effect plateaus. This is one of the universe's quiet habits. It allows quantities to increase long after their ability to change outcomes has flattened. The same thing happens with time. Human history is measured in centuries and millennia, spans long enough to feel almost abstract but still graspable. Stellar lifetimes extend this into billions of years, which already strains intuition. Beyond that, we enter durations so vast that adding more time does not produce qualitatively new behaviour. A trillion years and a quadrillion years are different numbers, but in many cosmic processes they lead to the same result. Everything that could happen has already happened. When time stretches far enough, it stops acting like a resource and starts behaving like an empty container. Processes do not become more complete because more time is available. They simply repeat or decay. Measurement continues to count, but completion has already been reached. This loss of distinction becomes especially clear when dealing with extremes of temperature. We are comfortable thinking about hot and cold because they map cleanly onto everyday experience. But the universe allows temperatures so high that ordinary matter cannot exist, where particles behave not as components of atoms but as fleeting excitations in dense energy fields. At these scales, temperature still has a numerical value, yet the difference between extremely hot and unimaginably hot stops changing the nature of what exists. Matter is gone either way. Structure is gone either way. The number increases, but the physical story does not. On the opposite end, extreme cold behaves similarly. As temperature approaches absolute zero, motion slows, energy differences flatten, and systems settle into their lowest possible states. Cooling something further still produces a number, but the system itself has already reached its simplest configuration. Measurement keeps going, while physical novelty has ended. Cold becomes colder without becoming meaningfully different. Size also breaks down when we move toward the smallest possible scales. We often imagine that shrinking things down will eventually reveal simpler components, smaller building blocks arranged neatly beneath the surface. But the universe doesn't behave like a set of nested objects endlessly subdividing. As we approach extremely small distances, the idea of size itself becomes unstable. At scales near the Planck length, the very notion of distance loses clarity. Space is no longer smooth enough to measure cleanly. Asking how big something is becomes similar to asking how long a shadow is in complete darkness. The question still exists, but the answer no longer corresponds to a physical property that can be isolated. What makes this especially strange is that mathematics does not fail here. Equations still function. Numbers can still be written down. Measurement survives formally even when it collapses conceptually. This creates a subtle illusion. Because we can calculate a value, we assume we understand what it represents. In reality, the calculation may only be telling us that our intuition has reached its limit, not that the universe has revealed something clear. Mass behaves in a similar way. We often rank objects by how massive they are, assuming that more mass always means more gravity, more dominance, more consequence. This is broadly true until mass crosses certain thresholds. Beyond those thresholds, adding mass changes very little about how an object interacts with its surroundings. A black hole with millions of solar masses and one with billions of solar masses behave almost identically from a distance. The number describing their mass grows enormously. but their external influence barely changes. Gravity saturates in a sense, not because it stops working, but because space-time geometry has already reached a regime where additional mass produces diminishing returns. Energy follows this pattern too. Enormous amounts of energy can be packed into regions so small that the distinction between more and much more energy loses practical meaning. Beyond certain densities, adding energy does not produce new forms of structure. It produces collapse, curvature, or dissipation. The measurement grows while the universe responds in the same way it already was. Even probability, a concept we rely on to manage uncertainty, begins to behave strangely at extreme scales. Over short times and small systems, probabilities feel intuitive. Over cosmic timescales, probabilities blur into inevitabilities. Events with incredibly low chances eventually occur simply because time is effectively unlimited. At that point, probability no longer helps distinguish what is likely from what is unlikely. Everything that can happen does happen somewhere, sometime. Probability remains mathematically valid, but its role as a guide to expectation disappears. All of these examples point to the same quiet conclusion. The universe allows measurements to grow or shrink far beyond the point where they help us understand outcomes. Numbers remain precise, but meaning saturates. This does not indicate a flaw in physics. It reveals a mismatch between human intuition and a reality that was never designed to be intuitive. The deeper lesson here is not that measurement fails, but that measurement was never meant to carry understanding on its own. Numbers are tools, not explanations. They describe relationships, but they do not guarantee insight. At extreme scales, relationships persist while intuition dissolves. The universe does not become mysterious because it hides information. It becomes mysterious because it no longer behaves in ways that scale smoothly from human experience. As we move further through these strange measurements, we'll encounter quantities that technically exist, but no longer correspond to anything that can be pictured, compared, or ranked in a meaningful way. Size will grow without dominance, time will pass without consequence, distance will increase without connection, and through it all, measurement will continue to work perfectly even as understanding quietly lets go. As measurement stretches further into these regimes, something subtle but profound happens. Comparison itself begins to fail. Comparison is the hidden engine behind almost all understanding. We grasp things by placing them beside other things, by deciding what is larger, smaller, faster, slower, heavier, lighter. But the universe allows quantities to drift into ranges where comparison no longer sharpens insight, it only repeats it. Once something is far enough, making it farther does not change what it means. Once something is massive enough, adding mass does not grant it a new role. Measurement keeps extending, but contrast flattens. This flattening is especially visible when we look at cosmic energy scales. Early in the universe, energy density was so high that the distinction between different forces dissolved. Electromagnetism, the weak force, and the strong force behaved as if they were variations of a single interaction. Here, energy was not just a number describing how hot or powerful something was. It defined what kinds of laws even applied. But as energy increases beyond that point in theory, nothing fundamentally new happens. The forces are already unified. The equations may allow higher energies, but the universe has already revealed everything those energies can do. Beyond a certain threshold, energy becomes a number without a new physical story attached to it. This same phenomenon appears when we talk about speed. The speed of light is often presented as the ultimate limit, and for good reason. As objects approach it, time slows, lengths contract, and mass increases. These effects feel dramatic and counterintuitive, but they still form a coherent narrative. Yet once something is already travelling at or near light speed, pushing it closer to that limit changes almost nothing about how it behaves. The difference between 99.9% and 99.9999% of the speed of light is a massive numerical jump, but the physical consequences are nearly indistinguishable. Measurement explodes while experience stagnates. This reveals an important pattern. Many of the universe's most extreme limits are asymptotic. They can be approached endlessly but never crossed. Numbers grow without bound, but physical behavior approaches a ceiling. In these cases, measurement becomes deceptive. It suggests dramatic escalation where none exists. The universe quietly transitions from growth to saturation, and intuition struggles to notice the shift. Length scales show this pattern in reverse. As we move towards smaller and smaller distances, we expect finer detail, sharper resolution, more structure. For a while, this expectation holds. Atoms give way to nuclei, nuclei to protons and neutrons, protons to quarks, but eventually, shrinking distance stops revealing smaller objects and starts revealing instability in the concept of distance itself. Space no longer behaves as a smooth background. Fluctuations dominate. Measurement produces values, but those values describe probabilities rather than locations. At that point, asking how small something is no longer tells us where it is or what it is made of. Size becomes a statistical suggestion rather than a property. What makes this especially unsettling is that the universe never signals that we have crossed a boundary. There is no warning sign that says measurement stops being useful here. The equations continue seamlessly. Units remain consistent. It is only when we try to interpret the results that confusion appears. We realize that we are still measuring, but no longer understanding. Density offers another striking example. Density seems straightforward. Mass divided by volume. Increase the mass, shrink the volume, and density increases. But at extreme densities, new behaviors emerge that render further increases redundant. Beyond certain limits, matter collapses into states where additional compression does not create new forms of organization. Neutron stars, for example, reach densities where atomic structure is irrelevant. Pushing beyond that does not reveal finer layers of matter. It produces black holes where density becomes hidden behind horizons. At that point, density still has a numerical description, but it no longer corresponds to something observable. Measurement persists while access vanishes. Time, too, becomes strange when measured over enormous ranges. We often imagine time as a resource that allows processes to complete. More time means more opportunity for change, but the universe contains processes that exhaust their possibilities long before time runs out. Radioactive decay, stellar evolution, and even black hole evaporation all have characteristic timescales, beyond which nothing qualitatively new occurs. Once these processes have finished, adding more time does not produce new outcomes. The number increases, but the state remains the same. Time ceases to function as a driver, and becomes a passive backdrop. This is one reason why the far future of the universe feels so counterintuitive. We are accustomed to time being meaningful because we live in an era where change is rapid. But when time stretches far beyond the lifespan of any structure capable of change, it loses its role as a narrative device. Measurement still tracks it, but nothing listens. The same flattening happens with entropy. Entropy increases as systems evolve toward equilibrium. For a long time, this increase corresponds to visible changes. Order fades, gradients dissolve, motion becomes less directed. But once entropy approaches its maximum, further increases no longer alter the state in a noticeable way. The universe does not suddenly become more disordered in a way that matters. It simply remains near equilibrium. Entropy still has a value. It can still increase infinitesimally. But the physical meaning of that increase has evaporated. Even information behaves this way. Information is often treated as something fundamental, a measure of complexity or structure. But information requires differences that persist. When differences fade, information loses substance. You can still calculate information content, but it no longer corresponds to anything that can be stored, transmitted, or used. Measurement continues, but application disappears. One of the strangest consequences of this is that the universe becomes filled with quantities that are technically well-defined but functionally inert. Distances that cannot be crossed, times that cannot be used, energies that cannot do work, sizes that cannot dominate. Measurements describe a universe that still obeys every law we know, yet no longer behaves in ways those laws once helped us predict meaningfully. This exposes a hidden assumption we rarely question, that understanding scales smoothly. We assume that if we understand something at one scale, we can extend that understanding upward or downward indefinitely. The universe does not honor this assumption. It allows understanding to plateau. Beyond certain points, knowledge becomes repetitive rather than deeper. We learn the same lesson again and again, that more is not always different. There is a psychological discomfort in this realization. We are trained to equate larger numbers with greater insight. Bigger telescopes, higher energies, longer durations. Progress feels numerical. As this pattern repeats across more domains, it becomes clear that the universe is not hostile to understanding, but it is indifferent to how far understanding can be stretched. It allows us to measure relentlessly, to refine units, to extend precision by orders of magnitude. Yet it does not guarantee that these refinements will continue to map onto insight. At certain scales, the universe stops offering new behaviors in response to more extreme values. Measurement becomes a mirror reflecting our persistence rather than a window revealing something fundamentally new. One of the quiet reasons this happens is that many physical processes are governed not by linear relationships, but by thresholds. Below a threshold, change matters. Above it, systems saturate. Gravity, for example, dominates behavior once mass and density cross certain limits. Below those limits, increasing mass changes outcomes dramatically. Above them, spacetime curvature has already taken control. Adding more mass alters parameters, but not the overall story. The universe responds in kind, not in proportion. This threshold behavior is easy to miss because mathematics does not emphasize it emotionally. Equations accept larger numbers without complaint. They scale smoothly. They remain solvable. but physical interpretation does not always scale with them. The universe does not shout when a threshold is crossed. It simply stops behaving differently. Measurement continues to climb while novelty quietly ends. A similar effect appears in cosmic volume. We often think that a larger volume contains more opportunity for complexity, more interactions, more surprises. Up to a point, this is true. Larger regions contain more matter, more structures, more variation. But beyond certain scales, volume becomes empty rather than rich. Expansion spreads matter so thin that adding more space does not add more interaction. The number describing volume increases, but the universe becomes quieter, not busier. Size grows while activity fades. This inversion challenges a deep assumption that more always means more happening. The universe demonstrates the opposite. At extreme scales, more space means fewer interactions. More time means fewer changes. More energy means less structure. Measurement grows while the universe simplifies. Even causality begins to feel strained in these regimes. Cause and effect remain intact locally, but their ability to propagate weakens. Events occur, but they do not echo. A fluctuation arises, but it does not cascade into a chain of consequences. Measurement can describe the fluctuation precisely, but the fluctuation does not matter beyond itself. The universe becomes filled with isolated events that do not add up to history. This is where measurement most clearly reveals its limitation. Measurement excels at capturing isolated facts. It struggles to convey significance when connections dissolve. Numbers can tell us what happens, but not whether what happens matters, and in large regions of the universe, mattering itself becomes rare. One of the most striking examples of this occurs in discussions of infinity. Infinity appears frequently in cosmology, often as a way of expressing unbounded growth or endless extension. But infinity is not a number in the usual sense. It is a statement about limits, about the failure of counting to complete. When we say the universe may be infinite, we're not describing an enormous quantity. We are acknowledging that measurement itself cannot finish the task. Infinity marks the point where size stops being a thing that can be grasped at all. Yet even infinity does not guarantee richness. An infinite universe can be empty almost everywhere. It can repeat the same conditions endlessly without variation. Measurement can label it infinite, but infinity does not automatically imply diversity or complexity. Again, the number grows without delivering new meaning. The same caution applies to the idea of extremes in probability. When probabilities are extremely small, we often treat events as impossible, but over sufficiently long times or large spaces, even rare events occur. Probability stops guiding expectation and starts describing inevitability. Measurement still assigns a likelihood, but likelihood loses its predictive role. Everything that can happen eventually does. Probability becomes a bookkeeping tool rather than a guide to surprise. At this stage, something fundamental shifts in how we should interpret scientific descriptions. Science does not fail when it reaches these plateaus. It succeeds in showing us where its explanatory reach changes character. The equations still hold. The predictions still work. What changes is the role those predictions play in understanding. They describe, but they no longer illuminate in the same way. This realization helps explain why certain scientific frontiers feel abstract or unsatisfying to non-specialists. It is not because the ideas are too complex. It is because the universe itself becomes abstract at those scales. The lack of intuition is not a flaw in communication. It is a faithful reflection of a reality that does not align with human-scale reasoning. In a sense, these strange measurements act as boundary markers for human comprehension, not absolute limits, but zones where understanding must shift from picturing to accepting. We stop trying to imagine what numbers look like and start acknowledging that some quantities only exist meaningfully within mathematics. The universe allows this division. It does not insist that everything be visualizable. This also explains why metaphors eventually fail. We lean on metaphors to bridge intuition gaps, but metaphors rely on similarity. At extreme scales, similarity disappears. There is nothing in everyday experience that corresponds to space-time curvature near a singularity, or to distances that permanently isolate regions of space. Metaphors stretch until they break. Measurement survives, imagination does not. What emerges from all this is not a bleak conclusion, but a more honest one. The universe is not designed to be fully grasped. It allows partial understanding where conditions permit and resists it where they do not. Measurement is the thread that carries us through both regions. It does not promise comprehension, only consistency. As we continue deeper into these out-of-scale measurements, we begin to see a pattern repeating across domains. Whenever a quantity grows large enough to lose its ability to create new structure, meaning flattens. Size without influence, time without change, energy without work, probability without surprise, distance without connection. These are not failures of physics. They are the universe showing us that understanding is contextual. It thrives in regions where contrast exists and fades, where contrast dissolves. Measurement tracks both phases faithfully, even when interpretation lags behind. The final lesson hidden in these strange measurements is not about the universe being unknowable, but about it being selectively knowable. It reveals itself richly where scales intersect, where quantities compete, where change accumulates, and it grows quiet where scales separate, where quantities saturate, where change loses leverage. Measurement does not stop at those boundaries. It continues calmly, indifferent to whether we find its results satisfying. Numbers accumulate, units remain valid, the universe remains lawful. But understanding transitions from explanation to acknowledgement, and perhaps that is the most out-of-the-box truth of all, that the universe does not withhold meaning as punishment, nor offer it as reward. Meaning arises where conditions allow it. Measurement shows us exactly where those conditions end, even if it cannot carry our intuition with it the whole way. From here, the strange measurements stop feeling like puzzles to be solved and begin to feel like signposts, quietly indicating where human-scaled understanding gives way to something broader, colder, and far less concerned with whether its numbers make sense to us at all. As measurement advances deeper into these extreme regimes, a more unsettling realization emerges. Sometimes the act of measuring does not merely describe reality, but actively reshapes the story we tell about it. Precision gives the illusion of certainty, yet certainty is not the same as understanding. A number with many decimal places can feel authoritative, even when what it refers to is only loosely connected to anything physical. The universe allows us to calculate values that feel exact while quietly withholding the conditions that would make those values intuitively meaningful. This illusion becomes most obvious when we examine quantities that appear stable on paper but unstable in interpretation. Take mass, for example. We treat mass as a fundamental property, something objects simply have. But mass is not a single thing. It can arise from energy, from motion, from interaction with fields, from binding forces. Two objects with identical measured mass may behave in radically different ways depending on how that mass is distributed, how it interacts with space-time, and how it contributes to curvature. Measurement compresses these differences into a single number, and in doing so erases context. Context is what measurement gradually strips away as scales grow extreme. At human scales, context comes for free. A distance implies travel, a mass implies weight, a duration implies experience. But at cosmic or quantum scales, context must be reconstructed artificially, and sometimes it cannot be reconstructed at all. We can say how far something is, how long something lasts, how massive something becomes, without being able to say what these facts mean in practice. This is where measurement begins to create illusions rather than clarity. Numbers feel solid, units feel trustworthy. But the physical world those numbers point to has drifted beyond the conditions that once made those units intuitive. We continue to speak in meters, seconds, and kilograms because they are convenient, not because the universe recognizes them. The universe has no preferred units. It does not operate in kilometers or years. Those are translations we impose, and at extreme scales, translation becomes distortion. Consider time again, not as duration, but as resolution. At very short scales, time becomes grainy. Events no longer occur in a smooth sequence. Fluctuations dominate, cause and effect blur. We can still assign timestamps, still measure intervals, but the idea that one moment cleanly follows another becomes fragile. Measurement says time exists. Experience would say time has fragmented. Both are correct within their domains, but only one survives into the extreme. The same happens at the larger scales, where time stretches so far that its passage no longer produces difference. When nothing changes in a meaningful way, measuring time becomes an exercise in counting without consequence. Time is still there, but it has lost leverage. Measurement remains faithful to its task, but the universe has moved on to a regime where that task no longer carries insight. This disconnect is not accidental. It reflects a deeper truth. Measurement was invented for systems that evolve within gradients. Differences in temperature, energy, pressure, density, and motion give measurement something to latch onto. When gradients flatten, measurement loses traction. The universe does not forbid measurement in these regions, it simply makes it irrelevant. This is why some of the most precisely measured quantities in physics correspond to the least intuitive concepts: vacuum energy, zero-point fluctuations, renormalized constants. These numbers are essential for calculations to work, yet they resist interpretation. They exist because the mathematics demands them, not because the universe presents them as tangible features. Measurement here becomes bookkeeping rather than description. At this point, it becomes clear that the universe is not divided into measurable and unmeasurable regions. Everything can be measured in principle. the real division is between regions where measurement produces understanding and regions where it produces only consistency. Consistency is valuable. It ensures that predictions do not contradict themselves. But consistency alone does not guarantee meaning. This distinction explains why certain scientific explanations feel deeply satisfying, while others feel cold or incomplete, even when both are correct. Satisfaction comes from alignment between measurement and intuition. Discomfort arises when that alignment breaks. The universe does not care which reaction we have. It supplies measurements regardless. Another strange consequence of extreme measurement is that it reveals how much of our understanding depends on narrative. We naturally turn sequences of measurements into stories. This led to that, this caused that, this grew into that. But narrative depends on a symmetry. It requires beginnings, middles, and ends. At extreme scales, a symmetry fades. Events stop forming chains. Measurement still records occurrences, but there is no longer a story to tell about them. This is especially clear in discussions of the far future. We can measure how entropy increases, how energy spreads, how structures decay. But beyond a certain point, these measurements describe a universe that is no longer evolving in a narrative sense. Nothing is progressing toward something else. Everything that could happen has already happened. Measurement continues, but storytelling ends. The universe here is not broken, frozen, or empty. It is complete in a statistical sense. All accessible states are equally likely. No state stands out. Measurement faithfully describes this sameness. But sameness is not something the human mind is equipped to find interesting. The same flattening appears in the smallest scales, where uncertainty replaces structure. Measurement yields probabilities instead of positions, ranges instead of values. This is not a failure of technology. It is a reflection of how reality behaves when forced into extremely fine resolution. The universe does not offer sharper detail beyond a point. It offers fuzziness, not because it is hiding something, but because there is nothing sharper to reveal. This realization reframes the role of limits in physics. Limits are not walls, they are transitions. They mark where one kind of understanding gives way to another. Measurement does not stop at these transitions. It simply changes what kind of truth it can deliver. Perhaps the most radical implication is this: the universe allows us to measure things that do not correspond to anything observable, anything influenceable, or anything experienceable. These measurements are not mistakes. They are reminders that mathematics can outpace physical intuition. We can write numbers that reality accepts without offering us a way to feel what they represent. At first, this feels like a loss, but it is also a gain. It frees us from the assumption that understanding must always be visual, intuitive, or narratively satisfying. It allows us to accept that some truths are structural rather than experiential. And yet, even this acceptance has limits. There are regions where measurement becomes so detached from consequence that it begins to feel hollow. We calculate because we can, not because it reveals something new. Precision turns inward. Knowledge becomes self-referential. This is not where science ends. It is where science changes posture. It shifts from exploration to maintenance, from discovery to consistency checking. The universe does not open new doors indefinitely. It opens a finite set of doors and then offers corridors that loop endlessly without leading anywhere new. Understanding this changes how we should approach extreme measurements. Instead of asking what more they can tell us, we can ask what their silence tells us about the structure of reality. The silence is not emptiness, it is saturation. The universe has not run out of things to do. It has run out of ways to surprise us through scale alone. Bigger numbers do not guarantee deeper insight. Smaller numbers do not guarantee finer structure. Measurement continues to function flawlessly in a universe that has quietly moved beyond the point where numbers alone can guide intuition. And this brings us to the most unsettling and liberating conclusion of all. The universe is not obligated to make sense at every scale in the same way. It makes sense where conditions allow difference, interaction, and accumulation. Where those conditions vanish, measurement remains, but meaning thins. This is not a failure of curiosity. It is the universe showing us where curiosity must change shape, where understanding becomes less about building pictures and more about recognizing boundaries. Boundaries not of knowledge, but of relevance. We are still measuring. The numbers are still real. The laws are still obeyed. But the universe has gently stepped into regimes where measurement tells us less about what exists and more about how far our way of understanding can stretch before it must let go. And we are not done yet. As we push further into this territory, another deeply counterintuitive pattern becomes impossible to ignore. At extreme scales, measurement does not just lose meaning, it begins to generate false confidence. Precision becomes seductive. A value with many digits feels more real than one with few, even when those digits correspond to nothing that can ever be tested, observed, or interacted with. The universe allows this illusion to persist because mathematics itself does not care whether a quantity corresponds to something tangible. It only cares whether the relationships remain consistent. This is how we arrive at numbers that are technically correct but physically hollow. We calculate them because the equations demand closure, because leaving them undefined would break internal consistency. Yet the universe does not guarantee that every internally consistent quantity corresponds to a distinct feature of reality. Measurement in these cases becomes a language speaking to itself. It remains valid, but it stops pointing outward. A clear example of this appears in discussions of fundamental constants. We measure values like the cosmological constant with extraordinary precision, refining its digits again and again as instruments improve. But what does that number do? It does not describe a force that can be felt, or a particle that can be isolated. It describes a background tendency of spacetime itself. Beyond a certain level of precision, knowing that value more accurately does not change how the universe behaves in any noticeable way. Measurement improves, consequence does not. This exposes a subtle hierarchy that we rarely articulate. Not all measurements are equally meaningful, even if they are equally precise. Some measurements shape outcomes, others merely describe a backdrop, and some exist only to prevent contradictions in our models. The universe allows all three to coexist without distinction. This is where human intuition often misfires. We assume that more accurate measurement automatically leads to deeper understanding. But the universe repeatedly demonstrates that accuracy and insight can decouple. At extreme scales, accuracy can increase while insight stagnates. Numbers become smoother, but reality does not become clearer. The reason for this lies in how systems generate novelty. Novelty requires imbalance. It requires asymmetry, gradients, tension between states. Measurement thrives when these conditions exist because it can track how differences evolve. When those conditions fade, novelty fades with them. Measurement has nothing new to follow. It continues to report values, but those values describe a system that is no longer exploring new configurations. This is why extreme uniformity is so resistant to explanation. Uniform systems are mathematically simple, but conceptually empty. They contain no preferred directions, no favoured outcomes, no internal narrative. Measurement can describe uniformity perfectly, yet uniformity itself offers nothing to interpret. The far future of the universe is the ultimate example of this. We can calculate temperatures, densities, and expansion rates with remarkable accuracy. Understanding is not a single continuous curve that rises smoothly with better instruments and finer measurements. It is a landscape with peaks and plateaus. There are regions where small improvements yield large insights, and regions where enormous effort yields almost nothing new. Measurement does not warn us when we enter a plateau. It simply keeps working. The danger, then, is not that measurement fails, but that we mistake its persistence for progress. We continue refining numbers because refinement feels like movement. But movement in measurement space does not guarantee movement in understanding space. The universe allows us to walk in place indefinitely, if we insist on doing so. This is why some of the most profound insights in physics do not come from pushing measurements further, but from recognizing when further measurement will not help. They come from reframing questions, not sharpening answers. They come from asking what a quantity does, not just what its value is. At extreme scales, the most honest response to measurement is often restraint. Not because the measurement is wrong, but because its implications are exhausted. The universe has already told us what it can tell us through that parameter. Continuing to refine it changes nothing essential. This is a difficult lesson because it runs against the culture of accumulation. We are trained to believe that more data is always better, more precision always valuable. The universe quietly disagrees. It offers regions where accumulation yields diminishing returns, where insight saturates long before precision does. In these regions, the role of science becomes quieter and more philosophical. It shifts from extracting new behaviors to recognizing structural inevitabilities. It acknowledges that some features of reality are not puzzles to be solved, but conditions to be accepted. This does not diminish science, it deepens it. It reminds us that the goal was never to force the universe into human-shaped narratives, but to understand where those narratives apply and where they dissolve. And this brings us closer to the most unsettling conclusion of all. The universe does not care whether its measurements are interesting. It does not optimize itself for comprehension. It allows complexity where conditions permit and indifference where they do not. Measurement faithfully accompanies both states, recording abundance and emptiness with equal rigor. We are still not at the end of this exploration. There is still one more layer to confront, one final inversion where measurement stops telling us about reality and starts telling us about ourselves, about the limits of expectation, the boundaries of intuition, and the quiet truth that the universe was never obligated to make sense at every scale we can measure, and that is where the strangest measurements truly begin to speak. As this final layer comes into focus, measurement turns inward. The universe has not changed its behaviour, but our relationship to its numbers has. At extreme scales, what measurement begins to reveal most clearly is not the structure of reality, but the structure of expectation itself. We discover that many of the questions we ask were never purely about the universe. They were about how far our intuition could be stretched before it snapped. We like to believe that every number corresponds to a feature out there, waiting to be understood. But the universe allows us to compute quantities that do not map cleanly onto anything separable, local, or influenceable. These quantities exist because our mathematical descriptions require closure, not because reality offers a corresponding object or process. Measurement in these cases becomes a reflection of our frameworks rather than a direct window into nature. This is where the illusion of objectivity becomes most fragile. Numbers feel objective because they are shared, repeatable, and precise. But objectivity does not guarantee relevance. A quantity can be objective and still fail to correspond to something that matters at the scale we care about. The universe does not filter its truths by usefulness. It allows all consistent descriptions to exist simultaneously. One consequence of this is that some measurements become detached from causation. They describe states that do not meaningfully influence other states. In everyday physics, causation feels tightly linked to measurement. Change one parameter and outcomes shift. But at extreme scales, parameters can vary without producing new causal chains. Measurement records variation, but causation remains unchanged. The universe permits this disconnect without hesitation. This challenges a deeply held assumption that knowing more numbers means knowing more causes. At certain scales, causes are already maximally expressed. Additional precision does not uncover new levers. The system has no remaining degrees of freedom that matter. Measurement becomes an inventory of what cannot be changed. In this sense, extreme measurement exposes the universe as fundamentally conservative. Not in the political sense, but in the sense that it preserves its behaviour once limits are reached. It does not reinvent itself simply because numbers grow larger or smaller. It respects thresholds, plateaus, and saturation. Measurement does not compel novelty. Another subtle shift occurs in how uncertainty behaves. At human scales, uncertainty feels like ignorance waiting to be reduced. Better instruments promise clearer answers. At extreme scales, uncertainty becomes structural. It is not a temporary gap in knowledge, but a feature of reality itself. Measurement does not reduce it beyond a point, it quantifies it. This is especially clear in quantum contexts, where uncertainty is not a flaw, but a constraint. At this stage, it becomes clear why size stops making sense is not just a poetic phrase, but a literal description of how physical relevance decays. Size matters only insofar as it changes relationships. Once relationships stop changing, size becomes decorative. Measurement can still describe it, but description no longer informs understanding. The same applies to duration, density, energy, and even complexity. All of them matter only while they create differences that propagate. Once propagation ends, measurement turns into bookkeeping, accurate, consistent, and increasingly detached. This realization forces a quiet re-evaluation of progress itself. Progress in science is often imagined as an endless march toward deeper understanding, driven by better measurements. But the universe reveals a different structure. Progress is uneven. It accelerates in regions of contrast and stalls in regions of uniformity. Measurement follows progress faithfully but does not guarantee it. This does not mean that exploration should stop when plateaus appear. It means that exploration must change its goals. Instead of asking what is the value, we ask, does this value still matter? Instead of refining digits, we examine frameworks. Instead of pushing scales, we interrogate assumptions. At extreme scales, the most productive questions are no longer quantitative. They become conceptual. What counts as an object? What counts as an event? What counts as a difference? Measurement alone cannot answer these questions. It can only reveal where they become unavoidable. In this way, the universe uses measurement to teach us restraint. It shows us that not every number deserves equal attention, that not every calculable quantity carries equal insight. It invites us to distinguish between mathematical existence and physical relevance. This distinction is uncomfortable because it undermines a comforting idea, that reality is fully legible if we just measure hard enough. The universe does not reject legibility. It localizes it. It concentrates intelligibility where conditions allow it and withdraws it where they do not. What emerges is not a failure of science, but a maturity of perspective. We learn that understanding is conditional. It depends on scale, context, and the presence of meaningful differences. Measurement is necessary for understanding, but it is not sufficient. This brings us to the quiet center of the topic. The strangest measurements in the universe are not strange because they are extreme. They are strange because they reveal where our expectation that more measurement equals more meaning quietly breaks. The universe does not mock us for this expectation. It simply ignores it. It allows us to measure forever if we choose. It does not promise that the results will continue to feel significant, and that indifference is not coldness, it is consistency. The universe treats all scales the same. It does not privilege the human range where measurement and meaning happen to align. Seen this way, the breakdown of intuitive measurement is not a problem to be solved, but a boundary to be recognized. A boundary between a universe that produces stories and a universe that merely persists. We are approaching the point where this recognition completes itself, where the final implication becomes clear, that the limits revealed by extreme measurement are not limits of reality, but limits of the kinds of understanding we evolve to seek. And once that becomes clear, the numbers stop feeling frustrating. They become quiet. They tell us not what the universe is doing, but what it no longer needs to do in order to exist. And that realization carries us to the edge of this exploration, where measurement has done its work, and interpretation must decide whether to follow or finally let go. At this depth, measurement stops acting like a window and starts acting like a boundary marker. It no longer tells us what the universe is doing in any vivid sense. It tells us where our way of asking questions has reached its natural limit. This is not because the universe becomes vague or chaotic, but because it becomes too consistent. Consistency, when taken far enough, erases contrast, and without contrast, meaning cannot accumulate. What we often call extreme in physics is not extreme because it violates rules, but because it exhausts them. The laws of physics are remarkably efficient. They do not generate infinite novelty. They generate a finite set of behaviours that repeat under different scales and conditions. Measurement tracks these repetitions faithfully, but repetition itself does not feel like discovery. This is why, beyond a certain point, learning more does not feel like learning something new. We encounter the same pattern expressed through larger numbers, smaller intervals, longer durations. The universe does not escalate its creativity to match our curiosity. It simply continues obeying its constraints. At this stage, it becomes clear that scale is not a ladder. It is a terrain. Some regions are rich, textured, and full of structure. Others are flat, smooth, and resistant to interpretation. Measurement allows us to walk across this terrain, but it cannot change its shape. The mistake we often make is assuming that every region should be equally interesting if we measure it well enough. This assumption is not supported by reality. Interest arises where differences interact. When interactions fade, interest fades with them. Measurement does not fail in these regions, it simply has nothing left to amplify. This is why the middle scales of the universe feel so alive. Atoms, molecules, stars, galaxies, ecosystems, minds. These are regions where forces compete, where feedback loops exist, where small changes propagate into large consequences. Measurement here feels powerful because reality itself is responsive. At extreme scales, responsiveness vanishes. In the smallest scales, fluctuations dominate but do not accumulate. In the larger scales, stability dominates but does not evolve. In both cases, measurement continues to operate, but leverage disappears. Numbers describe states that cannot be nudged into something else. This reveals a quiet asymmetry in how the universe supports complexity. Complexity is not guaranteed by size, energy, or time. It is a temporary phase enabled by specific conditions. Measurement can identify those conditions, but it cannot extend them indefinitely. Once those conditions dissolve, the universe does not collapse. It simplifies, and simplification is not the same as emptiness. A simplified system can still be vast, energetic, and lawful. What it loses is the ability to surprise itself. Measurement records this loss without commentary. At this point, we can see that many of the largest, smallest, oldest, and most extreme measurements we talk about are not milestones in understanding. They are markers of saturation. They indicate that a particular variable has done all the work it is capable of doing. Beyond that, additional change becomes cosmetic. Numbers grow, but behavior does not diversify. This reframes how we should think about the future of knowledge. It is not a straight line toward deeper insight driven solely by better measurement. It is a process of discovering which questions remain productive and which have reached closure. Measurement helps identify both, but it cannot tell us which is which. That decision belongs to interpretation, and interpretation, unlike measurement, cannot be automated. It requires judgment. It requires recognizing when a number has stopped earning its place in the conversation. This is uncomfortable because it challenges the idea that science progresses simply by accumulating facts. In reality, progress also involves letting go of questions that no longer lead anywhere new, even if they remain mathematically well defined. As we move deeper still, something unexpected happens to the idea of extreme itself. extreme stops being a direction and becomes a condition. We usually imagine extremes as edges you approach by pushing harder, measuring further, refining more. But the universe shows us that many extremes are not edges at all. They are zones where pushing further does nothing except confirm what is already true. Measurement continues forward, but understanding circles back on itself. This is why some of the most precise measurements ever achieved feel strangely anticlimactic. They confirm what theory already predicted, but they do not open new conceptual doors. The numbers line up beautifully, and yet nothing changes in how we think about reality. Precision becomes confirmation, not transformation. The universe allows us to polish the same truth indefinitely without revealing a deeper one. This creates a quiet mismatch between effort and reward. Enormous technological, intellectual, and computational effort goes into refining values that ultimately do not alter the structure of explanation. Measurement becomes a maintenance activity, ensuring coherence rather than generating novelty. This is not wasted effort, but it is no longer exploratory in the way we intuitively expect science to be. At this point, it becomes useful to distinguish between two kinds of limits: limits imposed by ignorance and limits imposed by saturation. Ignorance-based limits invite progress. They promise that better tools will reveal more. Saturation-based limits do not. They signal that a variable has already expressed all the behaviors it can express. Measurement can continue refining it, but refinement does not unlock new regimes. Many of the universe's strangest measurements belong to this second category. They are not mysterious because we do not know them well enough. They are mysterious because knowing them better does not help. This is especially apparent when we examine how scale interacts with complexity. Complexity does not grow smoothly with size. It appears abruptly when conditions align and vanishes just as abruptly when they dissolve. Measurement can track size continuously, but complexity behaves discontinuously. There are narrow windows where size matters enormously, and vast ranges where it barely matters at all. Stars exist only within a specific mass range. Too small, and fusion never begins. Too large, and instability dominates. Within that narrow band, mass matters profoundly. Outside it, mass loses relevance. Measurement continues smoothly across all values, but the universe responds only within a narrow corridor. The same pattern appears with planets, chemistry, and even biological systems. Complexity blooms in constrained zones and disappears outside them. Measurement does not mark these zones clearly. It treats all values equally. Meaning does not. This is where our intuition often rebels. We expect the universe to reward scale. We expect bigger to mean more powerful, smaller to mean more fundamental, longer to mean more complete. The universe quietly refuses these expectations. It allows extremes to exist without granting them narrative significance. Another subtle inversion occurs when we consider how measurement interacts with explanation. Early in an investigation, measurement helps identify patterns. Later, it helps test models. But at extreme scales, measurement often arrives after explanation has already plateaued. We measure because we can, not because we expect insight. This creates the illusion that science is always moving forward when in fact it sometimes moves sideways. It refines, cross-checks, and stabilizes without deepening. The universe permits this stabilization because stability is not a failure mode. It is a natural outcome once a system's behavior space has been exhausted. At these depths, the most interesting question is no longer what is the value, but what role does this value still play? Many extreme measurements retain mathematical roles without retaining physical roles. They keep equations balanced without shaping outcomes. Measurement records them faithfully, even when the universe has stopped responding to them. This reveals an important asymmetry between description and causation. Description can continue indefinitely. Causation cannot. Once all causal pathways have been explored, additional description becomes archival. Measurement becomes historical rather than predictive. The far future of the universe exemplifies this perfectly. We can describe it with increasing precision, yet nothing in that description allows intervention, redirection, or surprise. Measurement becomes a chronicle of inevitability. The universe has chosen its trajectory not through decision, but through constraint. At the smallest scales, the same asymmetry appears in reverse. Measurement yields probabilities with astonishing accuracy, yet individual outcomes remain fundamentally unpredictable. Description is rich. Control is absent. Measurement tells us what cannot be known, not what can. This dual failure of control at both extremes is not accidental. It reflects a universe where agency is local and temporary. Measurement can identify where agency exists, but it cannot extend it beyond its natural domain. This realization subtly shifts the emotional tone of science. Curiosity becomes quieter. Ambition becomes more selective. The goal is no longer to conquer scale, but to understand where scale stops being a useful axis of inquiry. At this point, the phrase "size stops making sense" acquires its full meaning. Size does not stop existing. It stops being explanatory. It becomes a background parameter rather than a driver of behavior. Measurement continues to track it, but explanation has moved on. What remains is not ignorance, but clarity of limitation. The universe has shown us where numbers matter and where they merely accumulate. It has revealed that understanding is not proportional to magnitude. And this is not a depressing conclusion. It is a liberating one. It frees us from the obligation to chase extremes endlessly. It allows us to recognize that insight is concentrated, not distributed evenly across scale. This recognition also reframes how we should approach future discoveries. The most transformative insights may not come from pushing measurements further outward or inward, but from reinterpreting the ranges we already inhabit. From asking new questions about familiar scales rather than extending old questions into domains where they no longer apply. The universe has already shown us that it does not reward persistence alone. It rewards alignment between question and context. Measurement helps us test alignment, but it cannot create it. As we continue, the remaining continuations will take this idea even further, exploring how meaning collapses not just in physics, but in the very structure of explanation itself, and why the universe remains perfectly complete even when our measurements stop producing insight. Once we accept that extreme measurement often signals saturation rather than discovery, another quiet shift takes place. Explanation itself begins to thin. Not because we lack equations, but because equations stop distinguishing between possibilities that matter. The universe continues to obey its rules flawlessly, yet those rules stop generating outcomes that can be meaningfully contrasted. Measurement still tells us what is allowed, but allowance is no longer the same as consequence. This is where the idea of explanation subtly changes character. At human scales, explanation feels causal. We explain something by showing how one thing leads to another, how a change here produces a result there. At extreme scales, explanation becomes structural rather than causal. It tells us why nothing new happens, rather than why something does. Measurement does not reveal mechanisms anymore. It reveals constraints. Constraints are less emotionally satisfying than mechanisms because they do not feel active. They do not do anything. They simply prevent alternatives. Yet constraints are often the deepest truths the universe offers. They define the shape of what is possible long before any particular outcome occurs. Measurement at extreme scales increasingly points to these constraints and away from specific events. This is why many frontier measurements feel static even when they are extraordinarily precise. They confirm the presence of boundaries rather than pathways. They tell us that a quantity cannot exceed a certain influence, that a process cannot generate new structure beyond a certain point. That variation has already been exhausted. The universe does not hide this information. It presents it plainly. What frustrates us is not ignorance, but finality. But this finality is not an ending in time. It is an ending in explanatory depth along a particular axis. Measurement along that axis has done its work. Continuing to measure does not deepen understanding because there is no deeper behavior left for that variable to express. This leads to an important inversion. Sometimes the most extreme measurements are not the most fundamental. They are the most redundant. They repeat the same story with greater numerical emphasis, but without conceptual expansion. The universe does not forbid redundancy. It allows repetition to persist indefinitely. At this point, it becomes clear that many scientific misunderstandings arise not from incorrect measurements, but from misplaced expectations. We expect every measurable extreme to unlock a deeper layer of reality. The universe quietly disagrees. It offers layers, but only where conditions support differentiation. Once differentiation fades, layers collapse into equivalence. This equivalence is deeply unsettling because it undermines hierarchy. We like to think in terms of deeper and higher, more fundamental and less fundamental. Extreme measurement reveals regions where hierarchy flattens. Larger does not dominate smaller. Smaller does not underlie larger. Everything exists under the same constraints, expressing them with diminishing variation. This flattening is not emptiness. It is symmetry taken to its limit. Symmetry is often celebrated as elegance, but perfect symmetry eliminates distinction. Measurement can describe symmetry beautifully, but symmetry itself resists narrative. Nothing stands out. Nothing prefers one outcome over another. The universe appears to favor a symmetry only temporarily. It allows it to arise, explore its consequences, and then dissolve. Measurement tracks both phases impartially. It does not privilege the phase where understanding feels richest. That privilege belongs only to observers embedded within that phase. This realization reframes how we should think about knowledge itself. Knowledge is not evenly distributed across all scales of reality. It is concentrated where reality produces contrast. Measurement gives us access to all scales, but understanding blooms only where contrast persists. At extreme scales, contrast disappears either because everything becomes equivalent or because everything becomes unpredictable. In both cases, measurement continues to function, but insight thins. The universe does not stop making sense. It stops making stories. Stories require difference. They require sequences where one state leads meaningfully to another. Measurement at extreme scales often reveals states that do not lead anywhere new. They are stable, repetitive, or probabilistic without accumulation. Measurement records them. Interpretation stalls. This is why the far future of the universe feels conceptually complete, even though it continues indefinitely. Completion here does not mean perfection or finality. It means that all the explanatory work that can be done by certain variables has already been done. Time continues, space expands, but explanation does not deepen. Likewise, at the smallest scales, measurement reveals fluctuations that never coalesce into structure. They arise and vanish without consequence. Precision increases, but accumulation does not occur. Measurement becomes an inventory of ephemeral states rather than a map of evolving systems. What both extremes share is a lack of leverage. Leverage is what allows small changes to produce large effects. Where leverage exists, measurement feels powerful. Where leverage disappears, measurement becomes passive. It observes without steering. This is why human intuition struggles most at extreme scales. We are creatures of leverage. Our actions matter because we live in a regime where small interventions produce significant outcomes. Measurement evolved alongside this intuition. Outside that regime, both lose their footing. The universe is not obligated to maintain leverage everywhere. It only allows it where conditions align. Measurement does not create leverage. It only reveals where leverage exists and where it has evaporated. At this stage, the idea that size stops making sense becomes inseparable from the idea that impact stops scaling. Size still exists, measurement still reports it, but size no longer buys influence, novelty, or explanatory depth. It becomes a background parameter rather than a driver. This realization also explains why some of the most awe-inspiring numbers in physics feel oddly hollow once encountered. They impress momentarily, then fade. They do not integrate into understanding because they do not change how reality behaves. They mark extremes, not transitions. Transitions are where meaning lives. Measurement shines brightest at transitions. It dims in plateaus. The universe contains both in abundance. Understanding this helps prevent a subtle form of intellectual exhaustion. Without it, we keep pushing into extreme measurement expecting revelation, only to feel disappointment when none arrives. With it, we recognize that disappointment is a signal, not a failure. It tells us that a particular axis of inquiry has reached closure. Closure does not mean that reality has ended. It means that a certain question has finished doing useful work. This shifts the focus of exploration from how far can we go to where does going further stop helping. Measurement alone cannot answer this. It must be paired with interpretation, judgment, and the willingness to change questions. The universe will never tell us when to stop measuring. It will never say, "This number no longer matters." It will simply stop responding in ways that generate new insight. Measurement will continue to speak. Meaning will quietly leave the room. And recognizing that moment is not a defeat. It is one of the deepest forms of understanding available to us. It is the recognition that reality has shown us everything it can show us along a particular dimension. As we move toward the final continuations, we will confront the last implication of this idea, that the limits revealed by strange measurements are not limits of knowledge, but limits of relevance, and that the universe remains complete, coherent, and unconcerned whether we find those limits satisfying. At this stage, the universe has quietly forced a role reversal. Measurement no longer explains reality to us. Reality explains measurement back to us. The values we obtain begin to reveal not what the universe is doing, but which kinds of questions still have traction within it. This reversal is subtle, because numbers continue to arrive with the same authority they always have. Nothing in their presentation suggests that their relevance has changed. Only interpretation reveals the shift. What we discover here is that many measurements function like echoes. They repeat information that has already been fully expressed, amplifying it without adding detail. The echo grows louder, sharper, more precise, but it does not carry new content. Precision becomes resonance rather than revelation. This is why the universe feels increasingly quiet at its extremes, not because it becomes empty, but because it becomes redundant. Redundancy is not disorder, it is the exhaustion of variation. Measurement records redundancy faithfully, but redundancy resists explanation because explanation thrives on difference. This also exposes a misconception about fundamental physics. We often equate fundamental with extreme, assuming that the deepest truths lie either at the smallest scales or the largest ones. But fundamentality is not about scale. It is about leverage. A principle is fundamental if changing it would change many outcomes. At extreme scales, leverage diminishes. Changing parameters produces little difference. Measurement may still describe these parameters, but their capacity to shape reality has already peaked. This is why some constants feel deeply important while others feel oddly inert. Both can be measured with extraordinary precision, but only some sit at points where reality remains sensitive to their values. Others lie in flat regions of the universe's response space, where adjustment yields no new behaviour. Measurement does not discriminate between these cases. Interpretation must. As this becomes clear, we begin to see that the universe organises itself around efficiency rather than abundance. It does not generate infinite layers of novelty simply because it can. It generates enough variation to explore its constraints, and then it settles. Measurement accompanies this entire process, but it does not drive it. This has a profound implication for how we think about progress. Progress is not guaranteed by extending measurement outward or inward. It occurs when we identify variables that still have room to act. Once variables saturate, progress shifts away from them, whether we notice or not. The universe is full of such saturated variables. We continue to measure them because measurement is possible, not because insight remains available. This creates a lag between what we can do and what is worth doing. Technology advances faster than interpretation. Measurement outruns meaning. This lag explains why frontier science often feels simultaneously triumphant and strangely empty. We achieve feats of precision that would have seemed miraculous in earlier eras, yet the conceptual payoff feels smaller than expected. The universe is not withholding secrets. It has already told them. We are refining the punctuation. At this point, the role of uncertainty becomes especially revealing. In everyday contexts, uncertainty feels like an obstacle, something to be reduced. At extreme scales, uncertainty becomes informational. It tells us that no further refinement will restore predictability. Measurement stops promising clarity and starts offering honesty. This honesty is uncomfortable because it forces us to confront the idea that not everything can be turned into a usable explanation. Some features of reality exist without providing handles. Measurement can identify them, but it cannot turn them into tools. This is why the deepest insights at these scales often come from recognizing absence rather than presence. The absence of new behavior, the absence of sensitivity, the absence of leverage. Measurement reveals these absences by continuing to function normally in their presence. The universe does not mark these moments with drama. It does not signal completion. It simply continues behaving the same way regardless of how much more precisely we describe it. Measurement becomes a witness to sameness. This sameness is not monotony in time, but monotony in possibility. Many future states collapse into equivalence. Many configurations become interchangeable. Measurement can still catalogue them, but cataloguing does not imply consequence. This brings us to an important realization about complexity. Complexity is not the default state of the universe. It is a temporary condition enabled by imbalance. Measurement captures complexity well because complexity produces contrast. Once imbalance fades, complexity fades, and measurement loses its most fertile ground. The universe does not mourn this loss. It does not strive to preserve complexity. It allows it to arise, explore, and dissolve. Measurement records the entire arc without preference. This neutrality is difficult to accept because we are products of a complexity-rich era. We instinctively expect reality to remain interesting, but interest is not a universal property. It is a local one. Measurement in this sense is brutally fair. It treats interesting and uninteresting regimes identically. It assigns values to both with equal rigor. It does not distinguish between a universe teeming with structure and one drifting in equilibrium. It reports both with the same calm accuracy. This fairness reveals something essential about the universe's priorities. It has none. It does not optimize for intelligibility, beauty, or narrative. It optimizes for consistency. Measurement is the language of that consistency. As we approach the final layers of this exploration, the phrase size stops making sense, begins to feel almost understated. What truly stops making sense is the assumption that measurement should always produce insight. The universe quietly dismantles this assumption without ever breaking a rule. What remains is not confusion, but clarity of a different kind. A clarity that recognizes that understanding has a topology. There are peaks where insight is dense and valleys where it thins. Measurement maps the terrain, but it does not flatten it. This perspective transforms how we should think about future extremes. Instead of asking how far we can push measurement, we ask where pushing further still matters. Instead of chasing bigger numbers, we listen for diminishing returns. The universe has already given us the answer. It does not announce it. It encodes it in the way measurement gradually loses explanatory power without losing precision. And that is the quiet genius of reality. It allows us to keep counting even when counting no longer changes anything. We are now one continuation away from closing the conceptual loop, and then one final continuation to bring it home philosophically. By now, the pattern is unmistakable. Measurement never collapses, never contradicts itself, never runs out of things to count. What collapses is the expectation that counting must always lead somewhere. The universe continues to permit measurement long after it has stopped permitting escalation. This is not a flaw in our tools. It is a feature of reality that only becomes visible once we follow scale far enough. At this depth, it becomes clear that the universe treats extremes not as destinations, but as asymptotes. You can approach them endlessly without ever arriving somewhere qualitatively new. Measurement encourages pursuit by remaining responsive. Each additional digit feels like progress. Yet the physical response has already converged. The universe has settled into a pattern, and measurement is tracing its outline over and over again. This is why extreme science often feels paradoxical to outsiders. It appears obsessed with refining values that no longer change the story. From the inside, this refinement is necessary for coherence. From the outside, it feels stagnant. Both views are correct. Measurement must continue for consistency, even when interpretation has nowhere left to go. Here, another inversion emerges. We often assume that mystery increases as we move toward extremes. In reality, mystery peaks in the middle. Extremes are often less mysterious precisely because they are constrained. They offer fewer possibilities, not more. Measurement confirms this by showing how tightly behavior is boxed in once thresholds are crossed. At intermediate scales, small differences amplify. Measurement matters because outcomes are sensitive. At extreme scales, sensitivity disappears. Everything becomes either locked into inevitability or dissolved into noise. Measurement still reports values, but the universe no longer reacts sharply to variation. This is why size at a certain point becomes cosmetic. A black hole 10 times larger than another does not rewrite the laws of gravity. A universe 10 times older than another does not introduce new physical phases. A distance 10 times larger than the observable horizon does not create new interactions. Numbers increase, behavior does not. This does not mean that extremes are unimportant. It means they are complete. They have already expressed everything they can express within the rules they obey. Measurement continues to describe them because description is always possible. Explanation, however, has reached saturation. At this point, the role of imagination also changes. Early on, imagination helps bridge gaps between numbers and experience. We imagine distances, forces, durations. At extreme scales, imagination breaks down not because the universe is hostile to it, but because there is nothing left for imagination to connect to. Measurement produces values that no longer map to experience, analogy, or consequence. The universe does not correct us when we try anyway. It allows metaphors to stretch until they tear. Measurement keeps delivering results even as interpretation frays. The silence that follows is not failure. It is alignment. Reality has nothing more to say through that channel. This is where the most disciplined form of understanding emerges. Knowing when to stop translating numbers into stories, not because stories are false, but because they are no longer applicable. The universe does not operate in narrative space at its extremes. It operates in constraint space. Constraint space is calm. Nothing pushes, nothing resists. Everything persists within boundaries that are no longer contested. Measurement maps these boundaries with exquisite accuracy. yet boundaries themselves do not produce drama. This calmness is often mistaken for emptiness or meaninglessness. It is neither. It is completion. The universe has finished exploring variation along certain axes. It does not erase those axes. It renders them inert. This also reframes how we should think about unknowns. At extreme scales, many unknowns are not unanswered questions, but unaskable ones. Measurement cannot rescue them because the universe does not supply answers in that format. Precision does not summon meaning where meaning has no foothold. The universe is not teasing us. It is simply uninterested in extending complexity beyond necessity. It allows complexity to bloom where gradients exist and fade where they do not. Measurement follows along, documenting both phases without commentary. At this point, the strange measurements we encounter no longer feel strange. They feel honest. They tell us exactly how far a variable can matter and where it stops earning attention. They reveal that understanding is not infinite in every direction, even though measurement is. This realization quietly dissolves the anxiety that often accompanies extreme science. There is no hidden layer we are failing to reach by not pushing hard enough. There are regions where pushing harder only confirms what is already known, that nothing new happens there. This does not close inquiry, it redirects it. Instead of extending scale, we examine structure. Instead of refining digits, we refine questions. Instead of assuming depth lies at the extremes, we recognize that depth lies where change still propagates. The universe has been signaling this all along. It never promised endless novelty. It promised consistency. Measurement is the language of that promise. As we approach the final continuation, the picture becomes clear. The strangest measurements in the universe are not strange because they are incomprehensible, but because they are too complete. They leave no room for escalation, only for acknowledgement. One final continuation remains, where this idea resolves into its simplest form, not as a conclusion about science, but as a conclusion about expectation itself. What ultimately settles into place is a realization so quiet that it almost feels anticlimactic, yet it reshapes everything that came before. The universe never promised that every measurable thing would remain meaningful forever. It promised only that it would remain consistent. We are the ones who attached expectation to scale, who assumed that pushing farther outward or inward would always unlock a deeper layer of significance. The universe did not agree or disagree with that assumption. It simply continued behaving as it always had. At the end of this exploration, the strangest measurements are no longer those with the largest numbers or the smallest units. They are the measurements that remain perfectly valid while no longer changing anything we care about. They are the numbers that continue to exist after their role has ended. Not because reality is broken, but because reality has moved past the phase where those quantities could still shape outcomes. This is where the phrase "size stops making sense" finally reveals its full meaning. Size does not disappear. It does not become undefined. It becomes irrelevant. It stops functioning as a lever. It no longer pushes reality in new directions. Measurement continues to report it faithfully, but reality has already decided how it will behave regardless of further escalation. The universe does this repeatedly. It allows variables to grow until their influence saturates, then lets them keep growing anyway. From the outside, this feels strange, even wasteful. From the inside, it is inevitable. A system governed by fixed laws does not need infinite variation to remain complete. Once those laws have expressed everything they can express through a given variable, further change becomes redundant. This redundancy is not emptiness. It is not failure. It is completion without closure. The universe does not stop. It does not reset. It does not collapse into nothing. It simply continues under conditions where novelty is no longer produced by scale alone. At this point, measurement becomes almost meditative. It tracks a reality that has settled into itself. The numbers arrive calmly, consistently, without surprise. They tell us not that something dramatic is happening, but that nothing needs to happen anymore for the universe to remain exactly what it is. This is where many misunderstandings about science arise. We confuse the continuation of measurement with the continuation of discovery. But discovery depends on sensitivity. It depends on the ability of small differences to cascade into large effects. Once that sensitivity is gone, discovery changes character. It becomes about recognizing limits rather than transcending them. The universe is not withholding deeper truths at its extremes. It is expressing a deeper truth through silence. It shows us that understanding has a topology, that it rises and falls depending on context, and that no amount of numerical refinement can force meaning to exist where conditions no longer support it. This is not a pessimistic conclusion. It is a mature one. It frees us from the idea that reality must always reward curiosity in the same way. It allows us to appreciate that some of the most important lessons are not about what more there is to find, but about where finding more stops changing the picture. In this light, the middle scales of the universe appear almost miraculous. They are the narrow band where measurement and meaning align, where size still influences outcome, where time still accumulates into history, where energy still builds structure, where complexity still feeds on itself. That band is not the default state of reality. It is a temporary one. The universe allows complexity to bloom, explore and fade. Measurement follows that entire arc without preference. It does not mourn the loss of meaning at the extremes. It does not celebrate the richness of the middle. It simply records what is. When we step back far enough, this impartiality becomes the most striking feature of all. The universe does not privilege the scales where observers exist. It does not preserve them. It does not optimize itself for understanding. It allows understanding where conditions permit and withdraws it where they do not. What remains, then, is not a mystery to be solved, but a relationship to be accepted. Measurement is a powerful tool, but it is not a promise. It can tell us how far a variable extends, how precisely a value can be defined, how consistently a law applies. It cannot guarantee that any of those things will continue to matter. This realization does not diminish science. It completes it. It shows us that the goal was never to make the universe endlessly legible, but to understand where legibility arises and where it fades. It teaches us that explanation has boundaries, not because reality is insufficient, but because relevance is. The strangest measurements in the universe are strange because they mark these boundaries so cleanly. They tell us exactly where scale loses leverage, where time loses narrative, where size loses dominance, where precision loses explanatory power. They do not announce this transition, they simply continue existing on the other side of it. And that is perhaps the deepest lesson hidden in all of this. The universe does not end where meaning ends. It continues smoothly, lawfully, indifferently. Meaning was never a requirement for existence. It was a byproduct of certain conditions, briefly present, intensely vivid, and never guaranteed to last. Measurement remains when meaning fades. Numbers persist. Laws hold. Reality does not notice the absence of interpretation, because interpretation was never part of its structure. The universe does not become empty at its extremes, it becomes neutral. Existence without emphasis, continuation without escalation, a state where nothing needs to change for everything to remain exactly as it is. This is not the failure of understanding. It is understanding reaching its natural resting point, a recognition that reality does not owe us endless depth, only consistency. That scale does not promise insight, only extent. And that sometimes the most honest thing measurement can tell us is that the universe has already finished saying everything it had to say through that particular dimension. Size does not stop existing, it stops mattering, and the universe remains perfectly complete either way.